Good morning, good afternoon, everybody. Welcome to another ARA Webinar Wednesday. I'm Jerry DiMaggio, your moderator for today's webinar, which is entitled Enhancing Road Safety Assessment with LiDAR Point Cloud Data, Accurate Detection and Severity Measurement of Pothole. My good colleague and friend, Dr. Abu Tahal, is presenting today. He's a great presenter for a young man. And over the past 4 years, he's conducted, you can look at his resume as I give you a few more details here. Over the past 4 years, he's conducted research projects that involve developing autonomous system, incorporating state-of-art sensors, which can be used to evaluate existing pavement conditions. I think you'll enjoy today's presentation. Abu received his PhD degree in civil engineering from the University of Cincinnati, his master's degree from Ohio University, and his doctoral science degree from Bangladesh University of Engineering and Technology. So with that, I turn it over to my good friend, Abu.
Thanks, Jerry, for your introduction. Good morning and good afternoon, everyone. Before I begin, I'd like to mention that this work was done as a part of my PhD research. So the topic itself is very special to me. So I would like to thank everyone who have shown interest in joining this presentation. So this slide shows the outline of the presentation. I will start with the background and then I'll describe the sensor that was used in this study, which is LiDAR. After that, I will dive into the methodology part, which will include pre-processing the LiDAR point cloud data, the object detection itself, the post-processing, and the implementation. After that, I will discuss the result of the study, which will include validating the accuracy of the algorithms that was developed as a part of this study. After that, we will discuss the field testing that was conducted to validate the algorithms. And finally, I will conclude this presentation with conclusions and future recommendations. All right. So we all know that a safe and efficient road network plays an important role in the overall economy of a country. And the safety and the efficiency of the road network really depend on the condition of the road network. Unfortunately, the condition of the road network do not remain the same over its service life. It experiences different type of distress, for example, multiple types of cracking, rutting, and other distresses as well. However, among them, pothole remains to be the most aggravating form of distress because it directly poses safety threat to the traveling public. It is reported that potholes are responsible for roadway crashes, and it is from the report it is observed that each year over $3 billion of dollars US dollars is spent to fix the damage to the vehicle due to the potholes. In addition, public agencies also face legal claims due to the incidents related to potholes, which cost a lot of money for them. Also, if a pothole is left unattended, it may lead to premature failure of the roadway. So, a timely detection of pothole location and the dimensions is extremely key for the transportation agencies. However, this task is not easy, and this is very challenging because of the vastness of the road network that the agencies are dealing with. So, what are the current practices when it comes to pothole detection? Unfortunately, still now, the transportation agencies are relying on the manual data collection, which means an inspector would go out looking for potholes while driving. Now, naturally, this method is extremely inefficient and also inaccurate. In addition, it poses safety because of the distracted driving. Therefore, the transportation agencies are opting for automation. However, the existing automated systems still are asynchronous, and also it requires the use of extremely sophisticated digital survey vehicle. Therefore, it becomes very expensive for pothole detection itself, and therefore the potholes are only detected only when the annual condition assessment is performed. Since the existing automations are extremely expensive, the manual survey remains to be the most prominent method, and as a result, a majority portion of the potholes remains to be undetected, and we still see road network like this. So based on the background, it is clear that we need a system or a pothole surveillance system that is affordable to the transportation agencies, yet it is extremely efficient and yet it is extremely efficient. Therefore, the objective of this study was to develop a surveillance system that is affordable to the transportation agencies, that is automated and real time, and that also use state-of-the-art technologies and algorithms. So the screen here you see shows the proposed system that was developed as a part of this study. The bottom image shows the top and the side view of the system that was developed, and the sensors that was used was LiDAR, and we also used a global navigation and satellite system for the georeferencing of the pothole, and we also had a camera just for the monitoring purpose. So before we begin, let's have a brief discussion or description about the LiDAR and its application. So LiDAR stands for light detection and ranging. It consists of sensors that sends out laser pulse towards the targeted object. The laser pulse hits the object and bounces back, which is captured by the sensor again. The time it takes for this back and forth of the laser pulse is used to measure the distance between the sensor and the object. And this process is replicated many times to create a detailed 3D representation of the object. Since its inception, LiDAR has been used in many applications. For example, in forestry, LiDAR is also heavily used in asset management. And in modern times, LiDAR is also being used in self-driving car for navigation purpose. So this is the LiDAR that was used in this study. It's a LiDAR manufactured by Ouster. LiDAR is named as OS1. It is basically a rotating, or in other words, it's a mechanical LiDAR. So basically the LiDAR sends and receives pulse as it is rotating. As a result, we obtain, because it's rotating and receiving the signals, we obtain a ring-shaped scans as shown in this figure below. So the LiDAR used in this study had 128 sensors. Therefore, we obtain 128 ring-shaped scans from each scan. The range of the LiDAR was 200 meters, and the field of view was 45 degree. The maximum frequency it can collect data is 20 hertz. However, in this study, the operating frequency was kept to 10 hertz. Before we use the LiDAR, we need to make sure the LiDAR is giving us accurate data. And to this end, we verified the accuracy of the LiDAR against 3 known objects. And the images shown here shows the method that was used to verify the accuracy of the LiDAR. So we have 3 known objects. We measured the dimensions of this object manually. We measured height, length, and the width. And then we took a scan of this object with the LiDAR. And finally, we also obtained the length, width, and the height from the point cloud data. So we compared the length, width, and the height. And this is the side-by-side comparison of the manual and the point cloud observation. And we can see the maximum difference in the length was only 0.2 inch. The maximum difference in terms of width and height was obtained to be 0.31 inch, which indicates that we can use this LiDAR in the field with very high confidence. The slide here shows the overall methodology or the overall workflow that was adopted in as a part of the framework. You can see there was many steps involved. However, we can summarize this step into three major components, including pre-processing of the data, then detection, and the post-processing. The pre-processing is basically processing the point cloud so that we can feed it into the detection model. The detection model is itself detecting the pothole from the LiDAR point cloud ring. And finally, we have post-processing to count the number of potholes, also obtain the dimensions from the point cloud data, and georeferencing. The first step of pre-processing was the appropriate ring selection. In the earlier slide, we saw the LiDAR is capable of generating 128 rings. Now, that can cover 200 meters. However, to capture something as small as pothole, we want to really focus on the area of the interest. Now, to this end, the rings were selected based on speed of the vehicle, so that we can focus on the pavement. At the same time, making sure that the optimum overlap between the subsequent scans, so that there is no area is missing. For an example, a vehicle move about 10 feet at 70 miles per hour. Therefore, the rings were selected in such a way that more than 10 feet is covered at 70 miles per hour with an overlap of half feet. Again, this half feet of overlap was extremely important so that no pothole is missed as the vehicle is moving. The second step of pre-processing was to correct the orientation of the rings. In the previous slide, we saw in the setup that the LiDAR was set at an angle. Therefore, we had to adjust the ring orientation, and the rings were adjusted after calculating the rotation matrix with respect to X, Y, and Z axis. Once each individual rotation matrix was obtained, the total rotation matrix was calculated using this following equation. Once we have the total rotation matrix, we could transform the point cloud by multiplying the rotation matrix with the point cloud itself. This slide here shows the overall framework of the pre-processing. So first we have the point cloud, the whole scan. Then this is after we select the appropriate rings. Then we adjust the orientation so that we can actually see the pavement. Once we correct it for the orientation, we trim the point cloud so that we can focus on the area of interest. And once we have, the final step was to extract the individual ring from the scan so that we can detect pothole from there. So once we have the pre-processing steps done, we detect the pothole from the LiDAR point cloud. And this slide here shows the overall workflow of the detection. So first, the LiDAR point cloud was rasterized using 640 bins in the horizontal direction and 320 bins in the transverse direction. So once the LiDAR rings was rasterized, it was fed into the object detection model as a batch. And finally, the object detection model would predict or detect the pothole from the rasterized data as a batch. So the object detection model was used to predict a pothole from the rasterized data. And in general, the object detection model can be defined as something that consists of convolutional neural network designed to identify and locate objects within images by learning features from the image. Now, there are many object detection model out there. However, in this study, we chose YOLO, which is you only look once object detection model, because of four features. First, YOLO object detection model is faster in terms of inference speed compared to other object detection model. It also has enhanced object detection accuracy. YOLO is also very easy and also very generalizable. Can be implemented in different frameworks. Also, it is the most important is it is open source. Therefore, it has the flexibility to be used and can be modified based on the project need. So once we select the model, we have to train the model so that it can detect potholes from the LiDAR point cloud. To this end, we trained the YOLO object detection model with approximately 9,000 pothole rings, point cloud rings. Among them, 50% of the rings had pothole and 50% of the rings was just background. Now, the background rings included different types of, let's say, section. For example, normal pavement sections, sections with rumble strips, and others. The main idea was to make sure that our model can detect pothole and can also detect that something that is not a pothole and identify from them. Once the model was trained, we tested the model with approximately 4,000 point cloud rings. And in that case, we intentionally mixed the test data set with 1,000 pothole LiDAR rings, and rest of it was background. Once a model was trained, the performance of the model was tested based on different evaluation metrics. First, we have precision. So what precision does, it indicates what percentage of the predicted positive instances are actually positive. Then we tested also the recall of the model, which is the percentage which indicates what percentage of actual positive instances were predicted correctly as positive detection. And finally, we have the overall accuracy, which simply shows the total number of correct prediction, which simply shows the number of correct prediction compared to the total number of prediction. And finally, we also had to take care of the inference speed, because this study we focused on real-time detection. Now, it is worth mentioning that we had to make sure that our model is performing really well in terms of all these evaluation metrics, because a good object detection model is supposed to be performing well in terms of all these parameters. So the final part of this algorithm was post-processing. And the first part of the post-processing was to count the exact number of potholes from a single scan. Now, a pothole can have many, a single scan can have many potholes. And we had to come up with an algorithm so that it can tackle any situation. For example, this image shows that the scan has 3 potholes, and we need to make sure that the algorithm that we develop also tells that, okay, we're getting 3 potholes from a scan. And to this end, we developed an algorithm that was that is shown in this flowchart. There are two main important things in these algorithms. First, we compare the overlap between the subsequent scan, and we compare the index number of the subsequent scan. So if the overlap between the subsequent scan was more than 20%, and then if the difference between the index number was less than equal to 2, then we considered the ring as part of the same pothole. Otherwise, we considered the ring as part of a different pothole. Next, once we know the count of the pothole, next we estimate the depth and the width of the pothole. And that was simply done from the width and the depth of the bounding box. So the width of the pothole was obtained from the width of the bounding box, and the depth of the pothole was obtained simply from the depth of the bounding box. And this is the result that we can see. There's a correlation between the actual width and the estimated width, and we can see and also the actual depth and the estimated depth. From this figure, we can say in both width and the depth, we see fairly good agreement between the actual and the estimated depth. The estimation of length was a little bit trickier for the pothole. In this case, to obtain the length of the pothole, we first divided the whole scan into 8 subsections, and once we divided the 18 subsections, we calculate the average X value of each ring within each subsection. And finally, we obtain the length by subtracting the X value, the average X value of the nearest detected ring from the average X value of the farthest detected ring. And using this algorithm, we predicted the length, and we compared the length with the actual length, and we can see a very high coefficient of correlation between the actual and length that came from the algorithm. So therefore, we were pretty confident that the method that we came up with to estimate the dimension of the pothole can be used very accurately to estimate the dimensions. Final part of this study was implementation. So once we have the algorithm set up, we implemented the algorithm in ROS. The steps are illustrated in this flowchart. As indicated in the flowchart, the LiDAR and the GPS data were first collected as LiDAR and GPS topics, which was then fed into the detection algorithm. The detection algorithm then published 4 information, which included bounding box coordinates, latitude, longitude, GPS timestamp, and the LiDAR timestamp, which was then fed into the post-process algorithm. And finally, we obtained the georeference of the potholes and the dimension of the potholes. This is a snapshot of a typical result that was published as a part of the process. As you can see, we have information related to the depth of the pothole, the width of the pothole, the length of the pothole. We also have the confidence at which our model detected the potholes. We also have the number of rings associated to the pothole, and also the latitude and the longitude of each individual pothole. All right. So in the previous slide, we saw the training and the testing of the YOLO object detection model. And in this slide, we see the result of the testing from the testing of the object detection model as a confusion matrix. So a confusion matrix has 4 components. We have in the first box, we have true negative. The second box on the right, we have false negative. The box on the bottom left have false positive, and the box on the bottom right has true positive. If we closely look at the first row of the confusion matrix, we can see the true negative is 99.5%, which means our model was able to correctly identify the non-pothole instances 99.5% of the times, which is really great. And if we closely look at the bottom row of the confusion matrix, we have true positive of 99%, which means 99% of the times the model was able to correctly identify the potholes from the LiDAR point cloud data. The information in this confusion matrix was further utilized to obtain the evaluation matrix that was shown earlier in the slide. So we calculated a recall, precision, and overall accuracy, and it can be seen that for all the cases, the value is very close to 1, which indicates how accurate the model was in terms of predicting the potholes and also differentiating the potholes from the non-potholes. Right. So the next step was to validate the accuracy of the pothole count algorithm that was developed as a part of this study. So in this case, we chose a scan that has 3 potholes, and we tested the algorithm. So we would expect, since there is 3 potholes, we would expect that our algorithm also would show 3 potholes, and we would also hope that the lengths, widths, and the depths associated to each potholes are fairly correct. This is the result of the algorithm, the pothole count algorithm. So the first key thing to note here is our algorithm is showing 3 potholes, so which is good, which is what we expect. And we also have the side-by-side comparison of the length and width and the depth. So the maximum difference in terms of the length was found to be 1.73 inches. In terms of width, the maximum difference was almost 1 inch, and the maximum difference in terms of the depth was only 0.16 inch, which is, I would say, within fairly reasonable limits. And also, it is very important to note that we also have these LiDAR rings. We would expect that the LiDAR rings would be associated correctly to the corresponding pothole. So if you look closely in this LiDAR scan, for example, pothole 2 has, from the visual observation, we can see pothole 2 has 4 rings associated to it, and our algorithm also showed 4 rings associated to pothole 2. Similarly, pothole 1 had 7 rings associated to it from the visual estimation, and we can see 7 rings are also associated to the pothole 1 from the algorithm. So in conclusion, we were pretty confident that, okay, our pothole count algorithm can deal with a very complex situation and give us correct result. Now, once we once we tested the algorithms individually, and once we are confident that our every bits and pieces of the algorithm is working, we carried out actual field testing in order to evaluate the system that was developed as a part of the study. And our field testing can be separated into 2 major components. First, we evaluated the accuracy of the system at highway speed, which is 55 miles per hour. And in the second part, we evaluated the repeatability of the system, and that was done by comparing multiple runs at 55 miles per hour. And secondly, it was also done by comparing the results from multiple runs at different highway speed, which is 55 miles per hour and 65 miles per hour. So the whole idea was to Whole idea was to gain confidence of the system in terms of accuracy and also in terms of the repeatability of the system. So this is the first part of the field testing where we tested the accuracy of the system at 55 miles per hour. On a section that had 19 potholes. We chose the section specifically, we chose such section specifically just to see how our system does in a very complex scenario. Now, it is worth mentioning that the actual depth, width, and length of the potholes were collected from stationary measurement so that we can compare the dimensions coming out from the algorithm with the dimensions that was measured from stationary measurement. So this is the result of the first field test. The images here, the first on the top left shows the side-by-side comparison of the depth of all the 19 potholes, which is plotted on the x-axis. The the blue bar shows the predicted depth and the orange bar shows the actual depth. The image on the top right shows the side-by-side comparison of the width, and the image on the bottom shows the side-by-side comparison of the length. The most important thing to note here is the trend that we obtained. From the trend, it seems that the predicted and the actual depth, width, and the length are in very good agreement. The key thing to note here is that, all the 19 potholes were detected, which is excellent. So we have 100% detection, and the maximum difference in depth was observed to be only 0.2 inch. Width, the maximum error was observed to be 2.58 inch, and in terms of the length, the maximum error was observed to be only 2.63 inch. So when we plot the error of all the 19 potholes, we see some interesting observation. So this image here is the error for all the 19 potholes. And we can see that these errors are quite randomly distributed along positive and the negative direction. We see the same thing for the width as well. The errors are distributed in the positive, both in the positive and negative direction, and it is quite random. So we can conclude that the algorithm that we developed for depth and the width estimation, the error associated to it are random. Therefore, we can say that in future we can use this algorithm for depth and without any further modification. However, when in terms of the length, we plot the errors, we see there is a trend, and the trend is the errors were always on the positive side. If we look at this image below, we plotted the predicted versus the actual length, and we can see the errors are always slightly below the 1:1 line, which means the algorithm that we developed would always, in most of the cases, would slightly underestimate the actual length. And that is because of the nature the LiDAR was collecting the data. We have to keep in mind that the LiDAR rings are discrete and may not cover 100% of the pothole area. Therefore, there is always a chance that the algorithm would always underpredict or underestimate the actual length. We compared the GPS location from stationary measurement and the run at 55 miles per hour. The maximum difference in terms of the location was found to be 7.5 feet with an average of 6.2 feet. So, which is, I would say, is a very reasonable limit. In the second part of the field testing, we tested the system the accuracy of the system at 2 runs at 55 miles per hour. And also we check the accuracy of the system of the 2 runs at 55 and 65 miles per hour, just to see how the system performs at different highway speeds. So the section where we performed the field testing had 4 potholes, and similar to the previous case, we calculated the actual depth, width, and the length of the potholes from stationary measurement so that we could compare the estimated dimensions with the actual dimensions. This slide shows here the result of the first 2 runs, which was conducted at 55 miles per hour. The most important thing to note here is that all the potholes were detected, and this is plotted on the x-axis. The y-axis shows the dimensions. In the top left we have the depth, in the top right we have the width, and in the bottom we have the length coming from different runs, and the comparison with the actual data. In this case, the maximum error for the depth was found only to be 0.2 inch. For the maximum error for the width was found to be 1.49 inches, and the maximum error for the length was found to be only 5.5 inches. We also compared the GPS location coming from run 1 and run 2, and from the 4 potholes we saw the maximum difference was found to be within 6.5 feet, which is again very close to the distance that we found in the previous test as well. This slide shows the result that was obtained from 2 runs at different highway speed. The first run was 55 miles per hour, and the second run was at 65 miles per hour. Now, similar to the previous case, we again see that in both runs, all 4 potholes were detected, and in this case, the maximum error in terms of the depth was found to be 0.47 inch compared to the actual depth. The maximum error in terms of the width was found to be 1.787 inch, and the maximum length was found to be 7.23 inch, which is relatively higher. But we have to also keep in mind that for that pothole, the actual length was pretty large, which is more than 25 inch. So therefore, the percentage of error was within a reasonable limit. We again compared the GPS location, the location of the potholes from the GPS information coming from the 2 runs. First, we have run 2, which is 55 miles per hour, and also we have 65 miles per hour. And the maximum difference in this case was found to be 8.3 feet, which is still a fairly reasonable limit. So based on the results that we obtained from different types of testing, we can conclude the following. First, it can be concluded that LiDAR can be used for pothole detection with a very high accuracy, and we have the validation result supporting this claim. We trained an YOLO object detection model, and the result of this study indicated that model can be used with very high accuracy for pothole detection, and it can be used in real time because of its very fast inference speed. The developed algorithm was tested with actual field testing, and the field testing indicated that we detected 100% of the potholes at different highway speed, and we also noticed that the estimated dimensions were within the reasonable limits compared to the actual dimensions. We also obtained from the results of the GPS location testing also indicated that the synchronized data from the algorithm can give us highly repetitive results in terms of the pothole location. And in summary, from this result, we can conclude that LiDAR offers the transportation agencies a viable alternative to the traditional automated methods. And it is safe enough to say that utilizing the system with LiDAR can actually enhance the pothole detection practices by increasing the efficiency and reducing the cost for the transportation agencies. Similar to any other system, this system is not 100% complete, and it can be further enhanced with future research. For example, the field testing we did not incorporate different weather conditions. For example, we don't know how the system would work during the rain or the snowy condition. We expect the system would work, but that should be validated with future testing under those circumstances. Also, we tested the system with limited speed limits. The study suggests that the system can be used with very high reliability at different highway speeds. Nevertheless, it is suggested that further testing should be done at different speeds to understand the effect of driving speed on the performance of the developed system. Finally, we're towards the end of the presentation, and credits must be given where it's due. I would personally like to thank University of Cincinnati for giving me this opportunity to work on this exciting project. Also, I would like to thank my supervisor, Professor Munir Nazal, for his guidance and his valuable directions, without which I don't think I would be able to achieve this work. With that, I would like to conclude this presentation and pass the baton to Jerry. Jerry.
Thank you, Abu. Excellent presentation. Very complicated, a lot packed into a 40-minute presentation. So we have received a numerous number of questions, and I'm certain we will not be able to get to all of them. So I want to first of all remind you, we'll get to Q&A in a moment, and I'll give you more details on how we'll address the ones that we can't speak about. I'd like to tell you a little bit about our upcoming webinars that we do this regularly. A few reminders. All of our presenters are either former or current ARA employees. And one of the objectives here, not only to share with the profession all the things that we have done and can do, but also to use for our professionals in their presentation capabilities and development skills. So a number of you have asked about the rescheduling from our Better Fuels group, and that unfortunately had to be postponed due to some personal emergencies. We're working on rescheduling that, so a number of you have inquired about that. If you want to get the latest information on our webinars, you see the ARA webinar Wednesday address right here, and then up and coming immediately in May 22nd, resiliency-based design, improving reliability under uncertain conditions. Dr. Ahmad Al-Hassan will be presenting that. Then on June 5th, always on a Wednesday, always at noon Eastern time, Ms. Laurie Strauss and Mr. David Hine will be presenting the use of permeable pavements. We've got a number of more exciting programs scheduled for you beginning in July through December. We're currently working on that as I speak. So as I mentioned, we've received a numerous number of questions. Abu, please try to be brief in your responses in the time that are allotted. And if you don't have your question addressed fully. Abu has been generous enough to provide his email address, and he'd be willing to receive supplemental questions, questions that you haven't thought about during the program for the next 24 hours, but make sure your questions are not consultant related and pertain to the topic that was discussed today. So the first question, current automated data collection vehicles can detect potholes through lasers. How is this LiDAR-based approach different from the current automated data collection approach, like collection through IRAN?
Okay. I'm not sure what the other laser means. If it is, I'm assuming the person is asking about the LiDAR that is used in other vehicle. So the main difference is in this study we used a LiDAR that is not a geodetic level LiDAR, and in most of the cases, the study in the practices, geodetic lidars are used, and the main difference in this study is the algorithm was set up in a way that that we can identify the pothole and also identify the dimension of the pothole in real time. So that's one of the biggest difference. And of course, I'm not sure about how the post processing is done in other systems, but we came up with a novel, or let's say a different approach that can be used to determine the potholes using the LiDAR.
What's the meaning? Next question. What's the meaning of rasterized? And I have to admit, I don't know what that means either.
Okay. The object detection algorithm cannot directly, like there are object detection algorithms that can directly get features from point cloud data. But the object detection algorithm that was used in this study can identify objects from images. So what we did, we rasterized, meaning we kind of converted the LiDAR point cloud into 2D histograms, so that can be used synonymously as image, and then image was fed into the neural network so that it can identify objects from the image.
Okay, thank you. So next question, did you train the model or did you use the previously trained model or a
Sorry, Jerry, again, your voice got
Did you
broke.
train the model or did you use a previously trained model?
No, we trained the model with custom dataset.
Okay, next question. So it's more of a comment, I believe, and a question. I like the simplicity of using YOLA on a rasterized line. Were there any comparisons made with other models that process the point cloud itself, like point CNN or point pillars?
Mm-hmm. We did not. That's a very good question. It will be worth seeing how the other models would perform. But it is worth mentioning that YOLO gave us the result that we needed, and we did not look further. But yeah, it is worth checking other models as well.
Okay, next question is, did you compare the capabilities of the sensor used in this study versus sensors used on passenger vehicles for self-driving applications? This is a reference to real-time distress. This is in reference to real-time distress detection.
You mean, so what was the question? The LiDAR used in passenger vehicle?
No, it was focused on sensors. So I'll read it again. Did you compare the capabilities of the sensor used in this study versus the sensors used on passenger vehicles for self-driving applications?
Mm-hmm.
This is in reference to real-time distress detection.
Yeah. So the LiDAR that is used in this study, I cannot say for sure, but this type of LiDAR I can say is used for self-driving car. So yes, we did not compare the result, but if the LiDAR is a rotating LiDAR or in other words, is a mechanical LiDAR and it generates ring, that LiDAR can be incorporated in this framework, but we did not compare.
Okay, next question. Can the program output location be converted to a KMZ file?
Honestly, I'm not sure what KMZ file is, but yeah, I'm not sure what KMZ file is.
Okay,
Sorry about that.
and that might be a good example. That was from Rob Davis. And Rob, if you'd like, you can follow up with an email. I don't believe we're going to be able to get to that based on a long list that we have. Next question that I have for you, Abu, is can the system pick up significant pavement cracks besides potholes?
This is a very hard question to answer. And so this is based on my assumption. LiDAR can detect anything that has elevation difference, but I'm not sure how it will perform in terms of detecting the cracks. So I think that will only further research can tell us the whole story.
Okay, and next question is somewhat related to the previous one about cracks. And this question is, were pavement cracks and joints a major source of false positives? Also, did accuracy differ between concrete and asphalt pavements, or differences in terms of the level of the pavement surface moisture?
Could you please repeat the question?
Sure. Okay. So were pavement cracks and joints a major source of a false positive? And
No.
then the
Yeah.
they were not. Okay.
Yeah, they're
And
not.
then the
Yeah.
second part, did the accuracy differ between concrete and asphalt pavements, or any differences noted related to the condition of the pavement?
No. Uh, uh, the different surface type would not make any difference because that's how our model was trained. So when we trained our model based on, let's say, 10,000 LiDAR point cloud, and that included different types of feature. For example, uh, um, uh, LiDAR point cloud from asphalt, LiDAR point cloud from concrete pavement. So no, to answer the question, no, it would not make any difference in terms of accuracy for the pavement surface type.
Okay, what about the moisture condition? That was
So the moisture condition, it depends how much moisture is there. Like if, let's say, the pothole is partially or fully filled up with water, we did not test that. I'm not sure about that, but if there is moisture, it will not matter. And yeah.
okay. That's fine. And you know, we're recognizing you can't know everything based on the level of study. So don't feel inhibited if you say we just haven't been able to study that. Future research. So unfortunately, we've only got 3 minutes left in the program, and unfortunately, or fortunately, we have quite a few additional questions. As I mentioned when we began the Q&A session, Abu will get back to all of you with a response. We've got everybody's questions in that chat. If you didn't get a chance to ask a question, again, the next day or so on this topic, feel free to have Abu's email address listed on slide 51. With that, next slide, please. So just a reminder, everybody who joined for the entire full hour program is entitled and will receive one PDH certificate for 1 hour of participation, as well as a PDF copy of today's presentation. Allow us a few weeks before you receive this information. And then if you have any questions, you have our email address, and our staff is very responsive. And I'm not referring to myself. Others handle this work. ARA, Applied Research Incorporated, this is our 45th year anniversary. Whoopie-doo. We're going to have a big cake and a big party. We're always looking for great people to join our team. One of our logos and mottos is science and engineering for fun and profit. And we hire and strive to hire the best of the best. So if you're interested in the current employment opportunities at ARA, you have send a brief resume and your contact information to the address that you see listed in this slide that you see 53, www.joinara@ara.com. I want to thank you on behalf of Abu, did a great job. Thank you all for joining us today. Have a blessed day and stay safe. Thank you all.